So in today's video, we're going to be looking at chapter 6.2, which looks at what it means for a set to be orthogonal. And then we're going to be looking at what it means for a set to be orthonormal. So first of all, let's take a set of vectors. We'll call them U1 through UP. Okay. For that set to be called an orthogonal set, it means that each pair of distinct vectors, so you're not going to take U1 with U1, you're going to take a distinct pair, so let's say U1 with U3. And if you take the dot product of the two, it's going to equal 0. So for every UI dotted with UJ, you're going to get 0 when I does not equal J. Okay, so each pair of distinct vectors is orthogonal, okay? They're orthogonal to one another, which means that ui dot uj is equal to 0 when I doesn't equal j, okay? So that means the set is orthogonal. Okay, so the dot product of each pair of distinct vectors is 0. Now, quick proof that we can do here. It turns out that if you have an orthogonal set of vectors, they're actually automatically linearly independent. So therefore, they will form a basis for the subspace of Rn that they span. Okay, so take S to be the p-dimensional subspace of Rn. So each UI exists in Rn, but we've got p vectors here where p is less than or equal to n. Okay, so we've got a p-dimensional subspace of Rn. Okay, that subspace of Rn is spanned by those p vectors. Okay, so you can take any linear combination of those p vectors and you would get a vector that is in S. But then it actually turns out that they are linearly independent. So the vectors in S are linearly independent. So therefore, if they span S and they're linearly independent, it must mean that they form a basis for S. And we actually call that basis for S an orthogonal basis because those vectors U1 through UP are orthogonal to one another, so they form an orthogonal basis. Okay. So the thing that we have to prove here is the fact that they are linearly independent. Okay, so let's take a linear combination of those orthogonal vectors U1 through UP. Okay, so I'm taking a linear combination of them. I'll let that linear combination equal the 0 vector. Okay, if they are linearly independent, it must mean that the only way that this equals 0 is if every CI equals 0. So C1 through CP is equal to 0. If any of them are non-zero, then it must mean that they're dependent. Okay, but we want to prove linear independence. So what I'm going to do is I'm going to dot both sides with U1. So I'm going to do C1, U1 plus C2, U2 plus CP, UP dotted with U1, and then I'm going to do the same thing to the other side, do 0 dot U1. So I've just dotted both sides with U1. The right side we can see would automatically be 0, okay? Then this left side, we're going to get C1, U1 dot U1 plus C2, U2 dot U1. Now we know that each UI and UJ are orthogonal to one another, which means that their dot product equals 0. So when I take u2 dot u1, I'm going to get 0. So that's going to eliminate that c2 u2 dot u1. Same goes with every other vector, okay? The only term that you are going to end up with on the left-hand side is c1 u1 dot u1, okay? Because all others, when you take a dot product of that vector with u1, it equals 0 because it forms an orthogonal set. And that must equal 0, okay? Now, because they span S, we are spanning a p-dimensional subspace, and they are linearly independent, okay? There is no way that we're going to have linear independence if any one of these vectors equals the 0 vector, okay? And we know that the 0 vector is never in a basis. So we're going to assume that none of these vectors are equal to 0, because as soon as one of those vectors equals 0, then it completely gets rid of the fact that they're going to be linearly independent and they're not going to form a basis for S. So to have any chance that they're going to form this basis and be linearly independent, we're going to assume that none of these p vectors are going to be 0, okay? So if none of those vectors are 0, it means that this dot product here is not 0. Because that dot product is not 0, but the whole left-hand side must equal 0, that must mean C1 is equal to 0, okay? If you keep doing this same thing, so come back up to what we've done here on this line, but instead, if I dotted both sides with U2 instead of U1, what I would end up with on the left-hand side is C2, U2 dot U2, and all other terms would go away because they would equal 0, like when I did U1 dot U2, that would be eliminated, etc. And on the right-hand side, I would still have 0. So if you kept doing this and dotted them through with U1, U2, U3, etc., you would actually find that every single CI equaled 0. So because every single CI equals 0, that must mean that U1 through UP are linearly independent. Okay, I will put a side note here. This is assuming that no vector is 0. Okay, because as soon as one of those is 0, we're going to have linear dependence anyway, because any set that contains the 0 vector is linearly dependent. So just to get rid of that whole scenario, we're assuming that none of those vectors is the 0 vector. You've got all non-zero vectors. They're going to span that p-dimensional space, and they're linearly independent. So therefore, they form a basis for S. Okay. The next thing, kind of going off the back of that, is an orthogonal basis for a subspace. So an orthogonal basis for a subspace W of Rn, so we're taking a subspace of Rn. An orthogonal basis of that subspace is a basis that is also an orthogonal set. So exactly what we have just said. If it is a basis, then it must mean that it's linearly independent and spans the space. But we want to put an extra condition on top of that, in that they form an orthogonal set. So every time I dot any of the two vectors together, any two distinct vectors together, I'm going to get 0. So an orthogonal basis for the subspace W of Rn is a basis for W, we'll call it U1 through UP, that is also an orthogonal set. Why do we like taking an orthogonal basis instead of just any random basis for a subspace? There is actually a reason for it, and it's because, and we'll look at something called projections in a second, but it's actually very easy to write any vector in that subspace as a linear combination of the basis vectors if they are an orthogonal basis. Okay, let's look at why that would be. If we take some random vector w that's y that's in w, okay, you've taken some random vector in w. If u1 through up is a basis for w, I should be able to write that vector in terms of the basis vectors, okay, by definition of a basis. So y is going to equal c1 u1 plus c2 u2 plus cp up. Okay, so I've written that random vector as a linear combination of the basis vectors. And I'm assuming that those basis vectors are orthogonal to one another. Okay. If that is the case, then it is actually very easy to find these coefficients when you take any particular y. Okay, so I can take any vector in w, and it's actually very easy to find that linear combination of the basis vectors if that basis is orthogonal. If that basis was not orthogonal, we would have to solve this as a linear system. So remember, if you ever have just a standard basis and you want to write a vector in that space in terms of the basis vectors, you would go ahead and put the basis vectors as columns of a matrix, and you would make the vector y the right-hand side. Then you would just reduce that matrix all the way down using Gauss-Jordan, and then you would be able to find out what that linear combination was. That's very time consuming. It's not the nicest thing to do, but we've done it many times. But there is a really easy way to do this if instead you use an orthogonal basis. Okay, you don't have to go through that whole Gauss-Jordan of a matrix or anything like that. All you have to do is a very simple calculation, and you can find out any linear combination of the basis vectors to find that vector. The way that we do this, it's very similar to what I just did when we looked at proving that the vectors were linearly independent. If I take, remember this formula for now, if I were to take y dotted with u1, okay, if I were to do that, my left-hand side would just be y dot u1. My right-hand side would be c1 u1 dot u1 plus c2 u2 dot u1. u2 dot u1 is 0 because they're orthogonal. And all the other terms would also be 0, okay, because I'm taking a distinct ui and uj and dotting them together. I know that that equals 0. So the only term I end up with on the right-hand side is c1 u1 dot u1. That means that c1 is y dot u1 over u1 dot u1. I can divide by u1 dot u1 because I know that none of those ui's are 0. So therefore their dot product is not equal to 0. Okay? So I can find c1. If I kept going with this, if I did y dot u2, okay, my left-hand side would be y dot u2. My right-hand side, c1 u1 dot u2. u1 dot u2 is 0. That term goes away. c2 u2 dot u2, we'd still have that term. c3 u3 dot u2, u3 dot u2 is 0, etc. So I would end up with, on my right-hand side, c2 u2 dot u2, which means that c2 is y dot u2 over u2 dot u2. So I can keep going, and I can actually find every single ci in my linear combination of the basis vectors to find y. So if I do that, it turns out that for, let's take the coefficient cj, it's just going to be the vector y that I start with. That's what I want to find the vector as a linear combination of those basis vectors. I'm going to take that vector y, I'm going to dot it with the jth basis vector and divide it by the dot product of that jth basis vector with itself. And I can do that for every single one of the coefficients and find those, and then I have my linear combination of basis vectors to give me y. Okay, so this is a really good formula to remember. Okay, it makes it really easy to go ahead and find any vector in that space as a linear combination of those basis vectors. Let's do a quick example. So we're going to take an orthonormal basis for our, orthogonal basis. Take an orthogonal basis for R3. And that's going to be 1, 0, 1, negative 1, 4, 1, and 2, 1, negative 2. Okay. If you want to go ahead and check this, you can. If you were to take any two of these vectors and take their dot product, for example, if we took the first two, if I took this vector dotted with this vector, okay, I would get negative 1 plus 0 plus 1. Give me 0. Okay, so if you take the dot product of any two of these vectors, you're going to get 0. So I want to express y is equal to 8, negative 4, negative 3 as a linear combination of the vectors in the basis. Okay, so I've got this orthogonal basis for R3, and I want to express this vector as a linear combination of those vectors. Okay, now they're an orthogonal basis, so I know that if I take a linear combination of them, okay, now C1 from what we've just said is y dot u1 over u1 dot u1. Y dotted with u1 is going to be 8 times 1 is 8, plus negative 4 times 0 is 0, so we're still at 8, plus negative 3 times 1 is going to be negative 3, so we've got 8 plus negative 3 is going to give me 5. And then u1 dot u1 is going to be 1 times 1 is 1, plus 0 times 0, so we're still at 1, and then 1 times 1 is 1, so we're going to be at 2. Okay? You can carry on doing this. So C2 is y dot u2 over u2 dot u2. So y dot u2, if you go ahead and do this, would be negative 27, and u2 dot u2 would be 18. You simplify that down, that is negative 3 over 2. And keep going, C3, okay, is y dot u3 over u3 dot u3. If you do that, you should end up with 18 over 9, which equals 2. So that tells me that y is equal to, coming back to what C1 and C2 and C3 are, I would get 5 over 2 times this u1 vector, minus 3 over 2 times this u2, plus 2 times this vector will give me my y vector. So I get y is 5 over 2 u1 minus 3 over 2 u2 plus 2 u3. That is way quicker to deal with than when we did Gauss-Jordan and reducing those augmented matrices. Okay, this is way faster to do. So that is like why we like these orthogonal bases. Okay, they make it so much easier to find that linear combination of basis vectors to find any vector in that subspace. Okay, now I want to look at orthogonal projections. So if we take some vector y, okay, that is in Rn, what we like to do is actually project it down onto a one-dimensional subspace to see where it would land. And we like to kind of decompose this matrix, this vector y, into a sum of two different vectors that are actually orthogonal to one another. Okay, this sounds very strange right now, but we'll kind of go through it. So if we take a y that is in Rn, what I want to do is to decompose y into the sum of two vectors that are orthogonal to one another. Okay. So if you think about it, the easiest way to think about it is in terms of like R2, okay? What you can basically do is if that is y, okay, what we want to do is to project it down to here. We'll call this, let's call this y hat. And let's call this z, okay? What we effectively want to do is to break y into two different vectors such that their sum is equal to that vector y, okay? But those two vectors are orthogonal to one another. So y hat and z, their sum is y, but y hat and z are orthogonal to one another, okay? We like to do this. This is used a lot in physics when you deal with forces and stuff. It can be very useful for that. It's kind of another way of dealing with it other than like when you deal with like angles and all that stuff. So that is when it's very useful to project onto a one-dimensional space. But we're going to look at how to do this. It's all to do with orthogonality and dealing with these orthogonal bases and stuff like that. So what we want to do is we want to project y onto the one-dimensional space spanned by u, which is just another vector in Rn, okay? So take this line here, okay, because a one-dimensional subspace, okay, is just a space that is spanned by one vector, okay? If a space is spanned by one vector, this one-dimensional space is spanned by one vector, which means that it's just all multiples of that one vector, which means that it's going to be a straight line, okay? In this case, I've actually drawn it as a horizontal line. It may not be horizontal, it can be in any direction, but it will be one line. Okay, so the one-dimensional space spanned by u is just going to be all multiples of u, which is going to form a line. So what we want to do is we want to take y and we want to project it onto that line that is spanned by u. Okay, so we want to find what that line will be. Now, as I said, the way that you do this is to decompose y into the sum of two orthogonal vectors. Okay, you're going to split it up into some multiple of u plus this vector z that's going to be perpendicular to that line that is spanned by u. Okay, so this is the line spanned by u. This is perpendicular to it. Okay, so z is orthogonal to u, it's orthogonal to every multiple of u, okay? And we want to split y into the sum of this multiple of u plus that vector z, okay? So what does that mean? Right now what we want to do is to split y into y hat plus z, okay? Y hat is a multiple of the vector u, which means it is on the line spanned by u that goes through the origin. Okay, in order for it to be a space, it has to go through the origin, otherwise it doesn't contain the zero vector. Okay, so what we want to do, y hat is the point on that line that is spanned by u where that will hit. So if you look at it here, this point here would be y hat, okay? It is the point on this whole line where y is projected onto, okay? And we're going to call it y hat. So y hat is just some multiple of that vector u, okay? What we want to do is we want to find alpha, okay, and we're going to find z, okay, because once we've found alpha, then we're going to know what y hat looks like, and then we can go ahead and find z, and then we're going to have the sum of these two orthogonal vectors that are going to sum to y, okay? So we've got this so far, and what we really want is for those two, sorry, that shouldn't be a vector, for those two to be orthogonal, okay? Now, what this means, if these two are orthogonal, if y hat is orthogonal to z, okay, I'm going to simplify a formula here just to make it easier so that we can find alpha. If y hat is orthogonal to z, okay, just take two vectors here just to make it kind of simple to see. That's the point y hat, that's the point z, okay? Now, y hat is just a multiple of u, okay? U is somewhere on that line, y hat is a multiple of it. So y hat also lies on that line, and it's the same line that u lies on. Take that to be the vector u. So if y hat is orthogonal to z, and we want it to be orthogonal to z because we want y to be split into the sum of two orthogonal vectors, if y hat is orthogonal to z, and y hat lies on the same line as u, that must mean that u is orthogonal to z. So that must mean that u dot z is equal to 0. Let's see what this tells us. So if u dot z is equal to 0, how else can I write z? Well, I've got this formula up here. Y is equal to y hat plus z. I can rearrange that. I can say that u dotted with y minus y hat is equal to 0. How else can I write this? Well, I can also say that y hat was just a multiple of u, okay? And we want to find what that multiple is. So I can rewrite this, and I can say u dot y minus alpha u dot u is 0, okay? Dot product is commutative. It doesn't matter which way round I put the vectors, so I'm going to move a couple of these around in a second. But if you were to rearrange this, okay, you can add alpha u dot u to both sides, okay? And then you can divide both sides by u dot u, okay? I'm going to switch these two around because it doesn't matter which way I do a dot product, okay? All you're doing is multiplying the entries and then adding them together, so it doesn't matter which way round you do it. But you should find alpha is y dot u over u dot u, okay? So that tells me y hat was alpha u, so it's going to be y dot u over u dot u multiplied by u, okay? So this thing here is just a scalar, and we're doing that scalar times u. So that tells me that y hat is that projection of y onto that line spanned by u. So that tells me the multiple of u at which that y hits. Okay, it's the projection of y onto that line. So let's say like u was here, okay, that would tell me the multiple of u that I have to take at which y would hit that line. And we're going to call that y hat. Okay, it's the point at which it hits. So what we actually say here, okay, so we know that they are orthogonal to one another, okay? We know that y hat and z are orthogonal to one another, and we know that y hat is the point on that line spanned by u, at which y is projected onto that line. So the way that we say this, okay, y hat, which is the projection, I'm going to call that line, that subspace spanned by u, I'm going to call it w. Okay, so what this says is y hat is the projection of y onto that subspace w that is spanned by u. So w is that one-dimensional subspace spanned by u. It is that line spanned by u. It's all multiples of u. So it's the projection of y onto that line, which we've just found to be y dot u over u dot u multiplied by u. Okay, where w is the line through the origin such that w equals the span of u. Okay, so it's just all multiples of u. And y hat is the projection of y onto that line. It tells you where it hits. It tells you at what multiple of u y would hit that line if you projected it down. So y hat is called the orthogonal projection of y onto u. Okay, it's actually y onto that subspace spanned by u. So you could call it the orthogonal projection of y onto w if you wanted to, but they tend to say onto u. It's just the space spanned by u. And z, okay, remember y hat plus z equaled that vector that we started with. Z is just the component of y that is orthogonal to u. Okay, it's orthogonal to u. It's orthogonal to that y hat. Okay. Now, let's do a quick example of this so we can see this in action and how it's used. So, let y equal this vector 1, 7. We want to compute the orthogonal projection of y onto the line through -4, 2 and the origin. Okay. So I want to find, if I projected y onto that line that is spanned by u, where is it going to hit? Okay, so let's say u is going to equal -4, 2. Okay, and we want to see at what point on the line spanned by that vector, where that line goes through the origin, at what point is y projected onto that line? Well, y hat, which is the point that it's projected onto, is y dot u over u dot u multiplied by u. So y dot u is going to be 10 over 20. 20 is u dot u. It's u dotted with itself. And then multiplied by u. So that equals 10 over 20 is 1/2, so that's going to be -2, 1. So that is the point on the line spanned by u that y is going to be projected onto. Okay. If I wanted to write y as the sum of two orthogonal vectors, z was just y minus y hat. Okay, which is equal to 1, 7 minus -2, 1. Which is going to give me 3, 6. So y, which is 1, 7, is equal to y hat plus z. These two vectors are orthogonal to one another. So I have split this vector in R2 into the sum of two vectors that are orthogonal to one another. This vector here is the point on the line spanned by u, negative 4, 2, at which y is projected onto that line, okay? And then the way that I can present y is as the sum of that vector plus another vector that is orthogonal to it, okay? And you can see that these two vectors are orthogonal. If you take their dot product, you're going to get 0, okay? The other type of question you may get in this situation is to find the distance between y and the line spanned by u. So if you want to find the distance between this vector and the line that is spanned by this vector, and you want to find the distance between the two, at this point, it would be a great time to open your textbook and look at page 342, okay? There is a figure 2, at the top of page 342, which shows you exactly what I have been talking about, okay? As saying that y is the sum of these two vectors, okay? And saying the projection of y onto that line, and it's represented that line and all that stuff. So it's actually got a very good picture at the top of page 342. If we want to find the distance between the vector y and that line spanned by u, okay? The shortest distance between y and that line spanned by u is finding the distance between y and y hat, okay? That is the shortest straight line distance between that vector y onto that line, okay? It's the shortest straight line distance. If you look, that distance would be the same as the magnitude of z. Okay, if you look at that picture, the distance between y and that line, the shortest distance, that straight line distance, would be the same as the magnitude of z. So if I want to find the distance between the vector y and the line spanned by u, okay, the shortest straight line distance would therefore be the distance between y and y hat, the point at which y is projected onto that line. Okay, so y minus y hat and take its magnitude. And that's the same thing as the magnitude of z, if you look at that picture. Okay, we found z in this case was 3, 6. So if I take its magnitude, I'm taking the square root of 3 squared plus 6 squared, which is the square root of 9 plus 36, which is 45. If you square root that, you can also write that as 3 root 5. Okay. So as I said, if you kind of want to see what this looks like, that diagram right at the top of page 342 is a great resource for you to kind of visualize what's going on here with these projections. Okay, I want to pull this back to what we were just doing when we were looking at writing a vector in terms of a basis of a subspace where that basis was an orthogonal set. Okay, so if we come back a few slides here. Okay, that was still an example. Let's come back a few more. Here we go. Okay, what I was doing here was I was writing this vector y in W, so it's a subspace of Rn. It could be Rn, but we'll take it as a subspace of Rn. And I was writing y as a linear combination of the basis vectors for W, where those basis vectors were orthogonal to one another. Okay. And then I said that it was really easy to do that because we can find C1, C2 through CP really easily by using dot products. And so we liked using an orthogonal basis just because it was way easier to do these calculations and we didn't have to deal with a Gauss-Jordan reduction of some augmented matrix to find C1 through CP. So we like to do this. But if you remember, when we did this, each of those CIs or CJs could be written as this. This is exactly what we were just doing when we did that projection. Okay. When we do this, okay, because this formula here for that multiple of a particular uj, okay, is exactly the same as what we had when we were just dealing with projections. So when you write a vector y in terms of its orthogonal basis, what you are effectively doing here is decomposing y into the sum of these p different orthogonal projections onto p different one-dimensional spaces. Okay? So if you think about it, for each one, what we are doing here is saying, okay, I want to find the projection of y onto the line spanned by u1. Where does it lie on that line? Okay, when I project it down onto the line spanned by u1, where does it hit? This term here, if I take y and I project it down onto the line spanned by u2, where does it hit? And you can do this p different times. So what you have done here, okay, exactly the same as we did with orthogonal projections, because it's the same formula, you are decomposing y into p different orthogonal projections, however many basis vectors you have, okay? You're decomposing it into p different orthogonal projections, and each one will tell you where y will get projected down onto that one-dimensional space spanned by that particular basis vector, okay? They have, again, another great diagram that I'm not going to attempt to draw because they're much better at it than I am. If you look at page 343, they have done this in the two-dimensional case, okay? So they've done this for R2, and they have shown you what this looks like. If you were dealing with a two-dimensional case, what you'd actually end up with, if I wanted to write y in terms of some orthogonal basis u1 and u2 for R2, so if I take u1 and u2 are an orthogonal basis for R2. Okay, and I wanted to write y in R2 in terms of these basis vectors. I could say that this was equal to y dot u1 over u1 dot u1 multiplied by u1 plus y dot u2 over u2 dot u2 multiplied by u2. Okay, this thing here tells me where y gets projected onto that line that is spanned by u1. This here tells me where y is projected onto the line that is spanned by u2. Okay, and they have got that really nice diagram on page 343 where they have demonstrated that. So if it's right at the bottom, it's figure 4 if you want to look at that. But that is literally what this does. So when you write a vector in terms of its orthogonal basis, and you write it as a linear combination of those orthogonal basis vectors, all you are doing is writing it as a combination of p different orthogonal projections onto these p different one-dimensional subspaces. Okay. Okay, the last thing I want to talk about here is orthonormal sets. So far we've been dealing with orthogonal sets where you take the dot product of any two distinct vectors in that set and it's going to equal 0. With an orthonormal set, it's very much the same. You take the dot product of any two of them and it's going to equal 0. But it has an extra property. So a set, call it U1 through UP, is an orthonormal set if it is an orthogonal set of unit vectors. Okay, what does that mean? Two properties here. First thing is that if I take UI dot uj, I'm still going to get 0, where I take two distinct vectors, so I doesn't equal j. But they are unit vectors, so the magnitude of each of these vectors is 1. Okay, so if I take the square root of the sum of the squares of the entries, I'm going to get 1. Okay. Classic example of this is when you want to take an orthonormal basis. Okay. An orthonormal basis is just an orthonormal set that forms a basis for a space, very much like an orthogonal basis. Classic example of that would be that standard basis for Rn. Okay, so let's take it back a step. An orthogonal basis, or orthonormal, sorry, orthonormal basis is a basis for a set, or for a subspace, sorry, that is also an orthonormal set. So as I said, a classic example of that is the standard basis for Rn. Okay, because if I take the dot product, just take the standard basis for R3. If you take the dot product of any two of those vectors, you're going to get 0. But the magnitude of each one of those vectors is just 1. So the standard basis for Rn actually forms an orthonormal basis. If you ever end up with an orthogonal set, but you want to make it an orthonormal set, all you have to do is normalize each one of the vectors. Okay, so if you've got this orthogonal set and you say, okay, I want to make it orthonormal, so I want to make sure that it's going to have a magnitude of 1 for each one of the vectors in that set, just make sure that you divide each one of the entries in that vector by the magnitude of the vector. That will normalize it. So let's say you had, we'll just take it for a particular vector. Okay, let's say you had 1, 2, 3. Okay, there's going to be other vectors in this set, but let's say that they are already orthogonal. So you take the dot product of any two and it's going to equal 0. But we want to make it an orthonormal basis. So you normalize each of the vectors. Let's say we wanted to normalize this vector. Find what the magnitude of this vector is, which would be the square root of 1 squared plus 2 squared plus 3 squared. So that's going to be the square root of 14. Okay, then all I have to do is to normalize this vector is to take each one of the entries and divide it by the magnitude of that vector. This vector now has magnitude 1. Okay, it's still going to be orthogonal to every other vector in that set. Okay, because dividing it by something isn't going to stop that numerator of the dot products equaling 0. So even when you do normalize vectors, it doesn't affect the orthogonality property. Okay, so you can go ahead, if you ever have an orthogonal set and you want to make it an orthonormal set, go ahead and take each vector and divide that vector by its magnitude. You will then end up with an orthonormal set because they will still be orthogonal to one another. They will just all have magnitude 1 at this point. It can actually be very useful, and we're going to deal with more of these types of matrices as we go along. It's actually very useful to have a matrix where its columns form an orthonormal set or an orthonormal basis for Rn if you're dealing with n by n. But it's actually very convenient to deal with matrices whose columns are an orthonormal set. So the way that you can tell if the columns of a matrix are orthonormal is taking the transpose of that matrix multiplied by the matrix itself. So A is an n by n matrix, and it has orthonormal columns, I should say. It has orthonormal columns if and only if, it actually works both ways, you take the transpose of that matrix, multiply it by the matrix itself, and it equals the identity. So a matrix has orthonormal columns, meaning that they form an orthogonal set, and each one of the columns has magnitude of 1. It has orthonormal columns if and only if, I didn't spell that right. Let me go ahead and rewrite that quickly. It's got orthonormal. It's got orthonormal columns if and only if you take the transpose of the matrix, multiply it by the matrix itself, and it equals the identity. Okay? It works both ways. So if you find that the transpose of a matrix times itself is equal to the identity, it means that the columns of A form that orthonormal set. So it works both ways. So if you ever find that that is the case, then you know that the columns of A are orthonormal. It's very, very useful to deal with orthonormal matrices, okay? We're going to go through a couple of properties of this. If you want to see a proof of this, it is in the textbook. I'm not going to go through it. It's actually a very simple proof. They've done it for a 3x3 matrix, just to kind of prove a point, but it does generalize to bigger matrices. So if you want to have a look through that, it's on page 345. It's about halfway down the page under theorem 6. They've called A U instead, but you can go ahead and look at that, but they've just done it for a 3x3. It's very simple. It just deals with the fact that they're orthogonal to one another. So it's actually a very quick proof. So go ahead and look at that. There are 3 properties of these matrices, of these orthonormal matrices, that are very, very useful. Okay? The first thing is, if A is an orthonormal matrix, which means that its columns form an orthonormal set, if I multiply that matrix by any vector x and take the magnitude of that resulting vector, okay, so let's say that when you took A times x, it equaled B, okay, the magnitude of B would equal the magnitude of that vector x, okay, so when you multiply by an orthonormal matrix, it does not change the magnitude of that vector. Okay, so that's the first reason why it's very useful. The next thing is if you have, let's say, A times x dotted with A times y, again where A is orthonormal. That's the same as just taking x dot y. This is actually really easy to see. The dot product is the same as taking the transpose of the first vector. So when you take a dot product, you've probably done this in, I think it's Calc 3 or something when you deal with this. If you take a dot product, it's the same thing as saying taking AX transpose AY. Okay, these two things are exactly the same. So when you do that, remember the transpose of a product is the product of the transposes flipped around. So this is the same thing as saying X transpose A transpose AY. A transpose A, orthonormal matrices, we know that that equals I. That's the same thing as saying A transpose Y. Again, taking the transpose of the first vector times the second vector is the same thing as taking the dot product of the two vectors. So that one's really easy to see as to why that's the case. The last property is if this thing equals 0, okay, the only way that x dot y is equal to 0 is if I can multiply each of these and it equals 0, okay? It's very simple to see because of what we've just proved. They're equal, okay? The only way one side is equal to 0 is if the other side is equal to 0. So we'll use that property later on down the line. But this is a very good property that when you take one vector, multiply it by an orthonormal matrix, and then you take the dot product of another vector multiplied by that orthonormal matrix, it doesn't actually change the dot product. It's just the same as taking the dot product of the two vectors. Okay. So it's actually a very useful property. That's all we're going to do for this video. Sorry, it is kind of a long video. I will give you some homework on Friday that deals with these orthogonal and orthonormal bases and stuff like that, so you can go ahead and get some practice with it. It does take some practice just to make sure that you're okay with all the algebra, but most of it is just very simple algebra once you understand what you're actually doing, especially with that projection stuff. So go ahead, ask me any questions if you do have any. I will be available during office hours or by email, so please ask me any questions you have, and I will see you in the next video.